Hello, students. Today we are going to discuss our chapter of thermodynamics in our lecture 5. In this lecture, we will briefly discuss about a new state function, that is enthalpy, and we will see how we are going to calculate the enthalpy change of a specific process and what is meant by enthalpy, that is H. So, firstly, we will start with the introduction of a reversible process. So, you guys have to understand that what is meant by a reversible process. A reversible process is such a path that cannot be done in practice. So, in reality, a fully reversible process cannot be attained. Suppose we are having a system which is at state A, let's suppose, and it is going to state B, and then again it is coming back from state B to state A. So when this kind of signature or the sign is going on, this double arrow, these are called reversible processes. So in case of reversible processes, A can be processed to B and B can come back to A, now, which is a reversible chemical reaction you might have seen. So what happens in this case? You can say that for example, if a gas is expanding against an evacuated space or vacuum. So in my last class, I have shared this fact that when P external, that is the pressure against the gas, is zero, the net work done by the gas will be zero. So when P external is zero, then the work done W will also be equal to zero. Since W is equal to minus P external into delta V. So when delta V will be equal to 0, W external will also be 0. So what happens in this case, that the minimum work that the gas can perform is W is equal to 0. Work done by the gas will be equal to 0 because P external will be equal to 0. So you have to understand that that is the minimum amount of work done by the gas. Minimum amount of work that a gas can perform is 0, and the condition is the external pressure is 0. So you might have understood the fact that under two conditions we can attain the work done, that is the minimum amount of work that can be done by the gas is 0. One is the P external is 0, and another one is the W, which is equal to 0. In case of dV, that is delta V, is equal to 0, then also the total amount of work done by the gas can be equal to 0. So that is the minimum amount of work that can be done by the gas. But then the next question arises that if the minimum work, that is W minimum, is equal to 0, so what will be the maximum work, that is W max, for a gas? What about the W max? So what is the maximum work the gas can perform on the surroundings? So to answer this, we have to see that the work done by the gas, the process which is carried out, if it can be performed in multiple steps or multiple stages, then the work done will be equal to 0. So if I take back you to the last class problem that I solved for you, like in this case, you see over here in the last class, I solved this problem. In the first step, A, the work done was minus 9 liter atmosphere. In case of path B, when I segregated the processes in the process into two different stages, firstly I decrease the pressure to 5 atmosphere, and then decrease it to 1 atmosphere. So instead of a single step, this was a one step process. And this was a two-step process. So in the last class, I showed that instead of one-step process, if I take a two-step process, then the work done was more, which was minus 13 liter atmosphere. So from here, we can see, or we can just have a conclusion that instead of one single step, if the process is carried out in two stages or more number of stages, then we will see the work done will be increased. So in a simple calculation, we can also show that the more amount of work can be performed if I even further increase the number of stages from 1 to 3 to 5 to 7, and more number of microscopic steps are involved, then the amount of work done will be more. So that is if we allow the gas to expand against a series of successively lower external pressure. So what I am saying, if I have to go from P1 pressure to P2 pressure, and instead of going directly from P1 to P2, if I take P3, then we come to P4. And in such a way, if I go ultimately to P2 after some 100 steps, then the amount of work done will be much more. So, in order to extract what is the maximal possible work that can be obtained from the process, what is the maximum amount of work that we are concerned about? So, then we have to incorporate more and more number of internal stages. So, at more and more number of successively lower external pressure will be introduced. And then the expansion would have to be carried out in an infinite sequence of infinitesimal steps. So here, these 1, 2, 300 all are finite numbers. But if I have to get the maximum work out of it, we will deal with infinite number of steps. So instead of 100, now we will have infinite number of steps where the pressures will be successively lower, and then each step will yield an increment of work, that is P delta V, and then eventually we will integrate it. So ultimately we are getting that W is actually P delta V, but this delta actually stands for a discrete function. So discrete means we are dealing with finite number of steps. But actually, to get the maximum work done by a reversible system, we will see that is the delta, capital delta, will be substituted by this integral delta, that is PdV. And since multiple steps are involved, in case of P delta V, we introduce a summation sign for discrete function. But for continuous this kind of function, we instead of summation, we do not use this summation. Instead of summation, we introduce this integration sign. So here we will integrate this PDV function from volume 1 to volume 2. So to get the maximum amount of work done in a reversible process, we will see that if for each step we are having a PDV amount of work. Since we have infinite number of steps, we have P1 delta V1, we have P2 delta V2, we have P3 delta V3, and so it will go on. And ultimately we will reach a Pn dVn. And to get the total amount of work, we will integrate the entire amount of expressions. So from if we consider the gas to be ideal in nature, we know that the ideal gas equation is PV is equal to nRT. So we can write P as nRT by V. So if we take this N beneath the V, we will have RT by V. For 1 mole of gas, V and V by N will be 1. So for N is equal to 1. So for 1 mole of ideal gas, P is equal to RT by V. And now if we substitute this P by RT by V over here, we actually get this equation, which is W is equal to integration V1 to V2 RT by V dV. So if we integrate this, we see that R is the molar gas constant and T the temperature. For an isothermal process, temperature is also fixed. So we will see the RT that is constant will be taken out of the integration. So it will be RT integration of dV by V, V1 to V2. And you know, since integration of dx by x is ln x plus k. So in case of W is equal to integration of dV by V, where V is V1 to V2, we will have RT ln V. And if we put the definite integral value, it will be RT ln V2 minus RT ln V1. So it will be RT ln of V2 by V1. Because for log, if we subtract between two logs, it will be divisible. So ultimately, we get this expression. The maximum amount of work done for a reversible process is RT ln V2 by V1. But as I have already told you that such a path which is corresponding to what is called a reversible process. So it cannot be realized in practice. It can be approximately as closely as desired. So although such a path it is which is corresponding to a reversible process, it cannot be realized in practice. So in reality or in practice, it cannot be approximated. So even though no real process can take place reversible, so in reality, we see there is no reversible process because it will take an infinitely long time. An infinitely long time is required for performation of an reversible process. So if you substitute the equation as W is equal to integration of P dV, we see for the ideal gas P is equal to nRT by V. For 1 mole of gas, N is equal to 1. So the molar volume is equal to the actual volume. So P is equal to RT by V. If we substitute this in the equation, we see RT for R is a molar gas constant and temperature for the gas is constant throughout the process for an isothermal procedure. So we will see it is RT integration of V1 to V2 dV by V. It's leading to ln V2 minus ln V1. So for two logs, if we subtract between two logs, the terms will be divided between each other. So it will be W is equal to RT ln V2 by V1. Even though no real process can take place reversibly, because in reality, for a reversible process, it will take infinitely long time for the performance of a truly reversible process. So, though reversible process play a very crucial role in thermodynamics, but the main reason for is because the Q reversible and the W reversible are state functions, which are important, and they can be calculated quite easily by this RT ln V2 by V1 equation. But many real processes take place sufficiently gradually that they can be treated as a quasi-reversible process for the easy calculation. So it's true that no reversible process can be attained in reality, But there are some processes physically present in our observable thermodynamic systems where they take significant amount of right time for completion, and that's why they are not truly or completely reversible, but they can be treated as almost reversible, and the calculation for those will also be easy. Here, this is a picture for easy demonstration of a reversible process. If you see, there are two kinds of states of the gas. In the first state, the gas is occupying 2.24 liter of volume at 10 atmosphere of pressure, and in the last step, the volume is 22.4 liter, which is the volume is getting expanded because the pressure is actually going down. That is 1 atmosphere. So for the first step, it was in a 20-liter atmosphere, and now it is going to a 202-liter atmosphere. In the second step, it is 28-liter atmosphere. Now it is coming to a 190-liter atmosphere state. And now if we such in this process, if we incorporate infinite number of stages, that's what it is becoming, making it reversible. So it will be a maximum work for a minus 52-liter atmosphere of work done, and against we get this plus 52-liter atmosphere of minimum work done. So if we see that in one stage it is minus 20, then it is minus 28, two stages, or three stages it is minus 33-liter atmosphere, and for infinite number of stages, the maximum work obtained is 52-liter atmosphere in negative value. Also, for step one stage, the compression study, if we are starting with 202-liter atmosphere of work, ultimately we are getting minimum amount of work, that is plus 52-liter atmosphere against an expansion and compression. So I hope there is a significant understanding of reversible processes. They cannot truly be they cannot truly be attained in our physical world, but there are some processes which take sufficiently sufficiently high amount of time that they can be considered as reversible process or semi or quasi reversible process. Now we will come to a new state function that will be introduced in this class, which is nothing but enthalpy. So for enthalpy, to start with, for a chemical reaction which is performing no work on the surroundings, that is the work done is equal to 0, the heat absorbed is the same as the change in internal energy. Because we are having this equation delta U equal to Q plus W. Now the work done by the gas is 0. So delta U will be equal to Q. But in many chemical process, there will be involvement of work in one form to another. So for an isothermal process where delta T is equal to 0, we will consider only the pressure volume work in this session. So if the process takes place at a constant pressure, then the work is given by P delta V. So the change in internal energy will be delta U is equal to Q plus W. Since W is equal to minus P delta V, so delta U will be Q minus P delta V. So you have to see that why Q is so important, because heat flow into the system or heat flowing outside of the system, they can be measured. This Q is a measurable quantity. But the delta U is an internal parameter of the system. Since delta U is an internal parameter, it cannot be directly measurable, or it is not a directly observable quantity. So the Q, that is the amount of heat that is passing between a system and the surroundings, is given by, if we rearrange this equation, delta U equal to Q minus P dV, we will have Q is equal to delta U plus P delta V. Now this means that if an exothermic reaction is accompanied by a net increase in volume under conditions of constant pressure. So the exothermic reaction is going on. So delta T will be 0 and there will be a net increase in volume of the gas. So delta V if is positive. So it is an expansion of the gas under constant pressure, obviously. So there will be some heat additional to delta U must be absorbed in order to supply the energy that is expended as a work done on the surroundings. If the temperature of the system is remaining unchanged because it is an isothermal process. For most of the practical purposes, we will see that the change in volume of the system are only significant if the reaction is accompanied by a difference in the moles of gaseous reactants or products. So only in this case, only gaseous reactants will be considered, not the solid or the liquid ones. Here, for your convenience, I have here a problem that is a for a reaction H2 gas plus half O2 gas will is equal to H2O liquid. What is the work done on the system at room temperature, that is 25 degrees Celsius and 1 atmospheric pressure? Before going to calculate this the answer of this problem, we will first see why this enthalpy term is introduced and what is its physical significance. If you see at constant volume, that is delta V is equal to 0, the heat absorbed at constant volume will be delta U will be QV. What is suffix over here is treated as constant in this case. So for delta V is equal to 0 because V is constant. So delta U, the change in internal energy will be QV. But most of the chemical processes or reactions that we carried out at our laboratories are not for constant volume. So constant volume chemical processes are not that much frequent, but constant pressure reactions are carried out in our laboratories. Because in flask or in test tube, you see there is a constant atmospheric pressure. So under constant atmospheric pressure, we perform reactions. But under constant volume, we do not or we perform very less amount of reactions. So delta U is equal to QV, but in flask or test tube, we perform reactions at a constant pressure. So we need to define another state functions which will be very much helpful for QP, that will be at constant pressure. Now, if we write this equation, delta U is equal to QP minus P delta V. Then P is put as suffix over here. That means P is constant. So delta U is equal to QP minus P delta V when the pressure is constant. QP is the heat absorbed by the system and minus P delta V is the expansion work carried out by the system. Now we will represent the initial state as 1 and the other state, the final step, as 2. So we have two steps, 1 and 2. Now delta U is equal to QP minus P delta V. So delta U means U2 minus U1. QP is constant because at a constant pressure, QP is the heat absorbed by the system. The pressure is constant, and for delta V, we will write V2 minus V1. So if we rearrange, this minus V2 will come to this side as plus V2, and this minus U1 will go to this side as plus U1. And this minus will eventually yield plus PV1. So we have on rearrangement of this equation U2 plus PV2 is equal to QP plus U1 plus PV1. Now we are getting QP as U2 plus PV2 plus U1 plus PV1. So we have these terms. So if we calculate QP over here, that is the heat absorbed by the system at constant pressure, we will have this expression U2 plus PV2 minus U1 plus PV1. So now we can define another thermodynamic state function, which is the enthalpy, which comes from the Greek word enthalpien. So heat absorbed by the system at constant pressure, that is called in thermodynamic language as enthalpy. This enthalpy comes from the Greek word enthalpien, which means to warm up or the heat content. So now we will define another state function as H is equal to U plus PV. So if we define H is equal to U plus PV as enthalpy, we ultimately get as this equation QP is H2 minus H1, which is nothing but delta H. Now Q is a path dependent function. As we know, it is not a state function, but H is a state function because it depends on U, P and V. Also, therefore, delta H is also independent of the path, since QP is also independent of the path. Now, for finite changes at a constant pressure, we can say from this equation H, we see delta H is equal to delta U plus delta of PV. So, if we operate delta on both sides, we have this equation as delta U plus delta of PV. Now, for delta H calculation, the pressure is kept as constant because delta H is defined as QP, the heat absorbed at a constant pressure. So, the P will be treated as a constant for this function PV and it will be taken out. So, we have delta H is equal to delta U plus P delta V. So we are ultimately getting this equation delta H is equal to delta U plus P delta V. So the change in enthalpy is equal to the change in the internal energy with an addition of the PV work by the system. So the heat absorbed by the system at constant pressure is called delta H. Delta H is nothing but QP. So delta H is negative for exothermic reactions. You have to understand like which involve heat during the reactions. So for an exothermic reaction where the heat is generated from the reaction, delta H will be negative. And the opposite is true for endothermic reactions, where the system is absorbing the heat from the surroundings. At a constant volume, that is delta V is equal to 0. In the first step, we have shown you that at a constant volume, that is delta V equal to 0, delta U is equal to QV. So when delta U is will be QV, and at a constant volume, since delta V vanishes, so delta H becomes equal to delta U. So the change in enthalpy and the change in internal energy will be equal in case of constant volume process or isochronic process. So from this series of equations, we have got very preliminary trivial equations which will be helpful for us to understand the concept of delta H, delta U, QV and QP. So delta H is QP, but in case of constant volume where delta V is equal to 0, delta H and delta U both merges to the same quantity, that is QV. So the difference between delta H and delta U is not usually very much important for systems consists of only solid or only liquid. So in case of solid and liquid, the change in volume is not that much significant. But the difference, however, becomes much significant in case of gases. Because in cases of gases, the volume expansion or the delta V terms is very much high in magnitude. So let's suppose we have two ideal gas where Va is the total volume of the gaseous reactant and we have Vb, which total amount of the gaseous product. We have Na as the total number of moles of the gases and we have Nb, which is the total number of moles of the gases which are the gaseous product. So in the first case, we have this ideal gas equation, which is PVA equal to NaRT. And for the second set of gases, which are the products, we have PVB equal to NBRT. This A suffix stands for the reactants. And for this set of gases which have suffix B are products. So PVA will be equal to NaRT and PVB will be equal to NBRT. So we have these two equations, 1 and 2. If we subtract these two equations, PVB minus PVA. So if we subtract equation 1 from equation 2, we have P into VB minus VA. On the right hand side, we will have NB minus NA. And for a isothermal process, since RT will be constant, it will be taken out. So if we substitute VB minus VA by delta V and NB minus NA as delta NG, we will have the equation P delta V. Will be equal to delta Ng RT. Where delta Ng will be referring to the number of moles of the gaseous products minus the number of moles of the gaseous reactants. So it is change in the number of mole of the gaseous components of the reaction mixture. Here in this case, no liquid or solid components will be considered. So if we substitute this value to the previous equation that we obtained between delta H and delta U, we will be having delta H will be equal to delta U. And now, since there was P delta V, and we have obtained that P delta V is equal to delta NGRT, so we have delta H equal to delta U plus delta NGRT. So have obtained the equation between the change in internal energy and the change in enthalpy. As they are the negative, the value that separates between these two is delta NGRT or P delta V. So with these informations in hand, we will try to calculate what is actually needed from our equation. So in this equation, we have H2, the problem that we sought after in the last slide, that is H2 plus O2 is giving rise to H2O. H2 is a gas, oxygen is also a gas, but the product water is a liquid. If we balance this equation, we will have H2 plus O2 will be equal to H2 plus half O2 will be equal to H2O. H2 plus half O2 will be resulting in H2, that is liquid. H2 is a gas and oxygen is also a gas. The total volume of the system is decreasing. So from that corresponding to 2 moles of gaseous reactants. Here, if you see the number of gaseous reactant, here in this case will be 1 plus half, which is 3 by 2. And here, in the case of number of moles of products, the gaseous number of reactants is 0. So delta Ng, which is change in the gaseous product and the reactants case in the moles, is delta Ng will be 0 minus 3 by 2, which will be equal to minus 3 by 2. So delta Ng is equal to minus 3 by 2. Since from two gases we are forming a liquid, that's why the delta Ng, that is change in the number of moles of the gaseous components of the reaction, is minus 3 by 2. We are obtaining 1 mole of water. You know that 1 mole of water corresponds to 18 grams, and 18 grams will be equal to around 18 ml. So a volume that will be so small in comparison to that of the reactants, because the gas, in case of gases, the amount of volume is much more high, but in case of liquid, the volume will be very much less. So in case of liquid system, we will ignore or neglect without any significant error in our calculation. So now we are dealing with a delta Ng, that is the difference in the number of mole, which is minus 3 by 2 or minus 1.5. Delta Ng will be equal to minus 1.5. So when it is negative, it is corresponding to a net contraction, that is the significant negative expansion of the system. Expansion, why it is negative expansion? Because in case of expansion, the number of moles will be increased. Since the gaseous moles numbers are decreased, that's why it is a contraction. So that means the surroundings is doing or performing work upon the system. The work is not done by the system, but the work is getting done on the system. Now, if we are considering the molar volume of the gas, that is V bar or Vm, both are used to denote the molar volume, which is V bar or Vm. So the molar volume at 25 degrees Celsius, that is room temperature, and at 1 atmosphere, it will be calculated, because you know, according to the basic law of gases, in case of ideal scenario, if we take an ideal gas at 25 degrees Celsius and 1 atmosphere of pressure, the gas volume is 22.4 liter. It is per mole, Vm or V bar. So according to the law of ideal gas law, we have three laws. PV is equal to constant, P varies as T as the Reynolds law, and V varies as T as the Charles law. So here we can incorporate the Charles law, and we will calculate the molar volume of an ideal gas as at 25 degrees Celsius as V varies as T. Since V varies as T, we will calculate the volume 2 V2 by V1 will be equal to T2 by T1. So if we have this V2 by V1 equal to T2 by T1 equation, so at 30 degrees Celsius, we can easily calculate what is the volume of the gas. So what is there? It will be 30, that is the volume that will be calculated. V1 is 22.4 liter per mole. So V2 will be V1 into T2 by T1. Here T1 is at 20 degrees Celsius, but since T is will be presented in Kelvin, so we will treat it as 293 Kelvin. And T2, that will be 25 degrees Celsius, at which we are performing the calculation, will be 298 Kelvin. So if we put these values over here in this equation, we will have 298 divided by 293 is 1.017 or approximately 1.02, which will be multiplied by 22.4 liter per mole. Eventually, with what it will yield around 22.8 liter of volume per mole. So V2 is 22.8 liter per mole. Now, if you have to remember the sign convention, if a flow of heat or performance of work that is happening that supplies energy, it will be positive. So if it is consuming energy, it is negative. Thus, if we are dealing with the work that is performed by the surroundings, that will diminish the energy of the surroundings only, because at the expense of its own heat, surroundings will perform some amount of work. So W surroundings will be negative, and that will increase the energy of the system. So W of the system or work done of the system will be positive. So work done by the surroundings on the system will be, the pressure is 1 atmosphere, and we are dealing with the change in the moles of the gaseous components of the gas mixture. So it will be 1.5 mole in negative, because delta Ng is negative. The work done with is by the surroundings on the system. And lastly, we have this change in the V, that is the V2, is 24.5 liter atmosphere of the system. So it will be delta Ng, it is P, and it will be delta V. So eventually it was 22.8 finally, and initially it was 22.4. So if we subtract between 22.8 minus 22.4, we are having 0.4 liter per mole. It is V2 minus V1. So we are having these three terms. 1 atmosphere that is corresponding from the pressure, minus 1.5 mole that is from the delta Ng, total number of change in the gaseous reactants or the components, and zero point 0.4 liter per mole is for the V2 V1 calculation, V2 minus V1. So we have 1.5 multiplied by 0.4, which is 0.6 in negative. So it will be minus 0.6 liter atmosphere. So minus 0.6 liter atmosphere is the total amount of change in the work, that is work done. So if we use the conversion factor, that is 1 liter atmosphere, what is equal to 1 liter atmosphere is approximately equal to 101.3 joule. So if we use this conversion factor over here, the amount of change in the energy of the system, so the change of the system increases its energy by how much amount of energy, which is 101.3 multiplied by 0.6. So it will be approximately 61 joule. So the work done using the conversion factor, bearing in mind the work performed on the system, supplying the energy to the system. So the work associated solely, that is with the volume change of the system, will be increasing its energy by this amount of energy, that is minus of 61 joule. This minus sign signifies the surroundings is doing some amount of the work on the system. So the internal energy of the system will be increased by 61 joules. So here I have taken up with another example, which is the reaction, that is H2 plus half O2 will be H2O liquid, is carried out at a constant pressure of 1 atmosphere and at a constant temperature of 25 degrees Celsius. So what quantity of heat, that is Q, will cross the system boundary? The boundary means what is separating the system from the surroundings. Now for this reaction, the change in internal energy, that is delta U, is treated as minus 281.8 kilojoule per mole, which is given. Now 281.8 kilojoule per heat of heat is there. The work performed by the surroundings supplies an additional energy, that is P delta V, is around this much of energy to the system. The total energy thus will be Q equal to this much. So now, because the most chemical changes I have said will be dealing with at constant pressure, so it would be tedious to have explicitly deal with the pressure volume work details. So that was described above. Now, fortunately, we chemists have found a way, that is definition of a new state function, that is delta H, which specifically deals with the corresponding changes at a constant pressure. So at a constant pressure, a new state function is arising as delta H, which is equivalent to QP, that is delta U plus P delta V. Because at a constant pressure from delta of PV, the P will be treated as a constant and it will be taken out from the system. Enthalpy will be hiding some amount and it will be saving it too. Now, there is a last problem of this session, that we will see how we can calculate. From this equation, we see that a hydrogen chloride gas, that is HCl, readily dissolves in water, releasing around 75.3 kilojoule per mole of heat in the process. If 1 mole of HCl at 298 Kelvin and 1 atmosphere of pressure occupies this much of volume, that is 24.5 liters, find the delta U for the system when 1 mole of HCl dissolves in water under this identical condition. Now, according to the question, you see that in the process, volume of liquid remains practically unchanged. The hydrogen chloride gas readily dissolves in water, and the atmospheric pressure, it have 1 mole of HCl, we are having occupying 24.5 liter of gas. So if we calculate delta U, yes, if you calculate a delta V, that is change in volume, it will be volume of the HCl liquid minus volume of the HCl gas. Now see, according to our assumption, since volume of the HC liquid is very much small in comparison to the volume of HCl gas. So in this case, if we neglect this term as and it is taking as assuming it to be zero almost, we will have only the volume of HCl gas, which is minus 24.5 liter. So delta V is this one. Now if we calculate W, which is the work done, it will be minus P delta V. P is taken as 1 atmosphere because it is taken as in under atmospheric pressure. So we will have minus of 1 atmosphere into minus of 24.5 liter. So we ultimately have the work done as 24.5 liter atmosphere. The work is positive here because it is being done on the system, because the volume is decreasing, because from a huge amount of HCl gas is getting dissolved to form a HCl liquid. That's why the dissolution of the gas into a much smaller volume of the solution. Now if we use the conversion factor, that is delta U of the that is 113 joule per mole, in this case we will calculate delta U is equal to Q plus W. The Q, which is actually given over here, that is 75.3 kilojoule per mole. So here we have 75.3 kilojoule per mole. And also we have this 4.5 liter atmosphere. And if we use the conversion factor, which is 1 liter atmosphere is equal to 0.1013 joule. It is per mole of the gas. So ultimately we will have around minus of 72.82 joule per mole. So that is the change in the internal energy of the system. So with this, I hope you understand, if the gaseous HCl could dissolve without any volume change, the heat released in this process, that is 75.3 kilojoule, would cause the system's internal energy to diminish by that same amount of energy, that is 75.3 kilojoule. But the disappearance of the gaseous phase will reduce the volume of the system, because with respect to the gas, the volume of the liquid will be very much small. So accordingly, the delta U, which is calculated over here, is around minus 72.82 joule per mole. So with this, we'll stop today's session. If you have any kinds of queries or doubts regarding any of the slides, you can go ahead and ask.